Good afternoon and welcome to this live event, how wastewater plants can cut costs and emissions with fuel cell technology. This is an opportunity for municipal operators and engineers to learn how wastewater treatment plants can become more sustainable and efficient with fuel cell technology. We'll showcase some of the latest technological developments, and you'll gain insight into how fuel cells can reduce greenhouse gas emissions, lower energy costs, and generate renewable power from biogas. It's an opportunity to discover how fuel cells can transform wastewater treatment operations and benefit nearby communities. Our presenter today is Anthony Leo, the Executive Vice President and Chief Technology Officer of FuelCell Energy. Tony joined FCE in 1978 and has held key leadership roles in research, development, and commercialization of electrochemical systems during his tenure. He is well known throughout the battery and fuel cell industry and has authored numerous papers, contributed to technical books, holds several U.S. patents, and has served as chairman of the American Society of Mechanical Engineers PTC 50 Fuel Cell Performance Test Code Committee, and as a member of the Department of Energy's Hydrogen and Fuel Cell Technical Advisory Committee. Tony is involved in managing advanced research and development, as well as the commercialization of the company's fuel cell products. And my name is Luke Lagus, editor of Municipal Sewer and Water Magazine. I want to thank everyone for attending and encourage you to ask questions as they arise. You can type those in through your GoToWebinar control panel throughout this presentation, and we'll answer them during our Q&A session at the end. And now I'll turn it over to Tony to get us started.
Thanks, Luke, and good afternoon, everyone. I'm Tony Leo from FuelCell Energy, and I would like to talk about the things that fuel cells can do for wastewater treatment plant operators. And first, I'd like to spend a couple slides just talking about the company for those of you who may not be familiar with FuelCell. Let me just get there. So FuelCell Energy, we're based in Danbury, Connecticut, which is where our corporate headquarters is, our R&D facilities. We have a manufacturing facility about an hour away from Danbury in Torrington, Connecticut. We have facilities just outside of Munich in a town called Taufkirchen in Germany for final assembly and service of our European installations. And we have a facility in Calgary, Alberta, Canada, that is doing R&D and manufacturing of our solid oxide cell technology. What FuelCell does is we use electrochemical platforms to produce low carbon or zero carbon power, to capture CO2, and to produce hydrogen. And if you look at the cluster of logos to the right of this slide, we have a variety of different customers, including utilities that sell power that buy power from our platforms, private companies that use our platforms for on-site combined heat and power generation, municipalities that install our fuel cells at wastewater treatment plants, which is obviously the focus of today's discussion. And we have been in business since the 60s. We have about 500 employees. And just under 100 of our platforms are in operation around the world. And when I talk about our platforms, we have two types of systems that we produce around two different types of fuel cells, both what are classified as high temperature fuel cells. One is the carbonate fuel cell, and the other is the solid oxide fuel cell. And as you can see from this slide, they have a mix of different features and capabilities. Some overlap. They're both very good combined heat and power platforms for making clean electricity. Carbonate can run on hydrogen and fossil fuel mixes. Solid oxide can run on pure hydrogen, and that's going to be important in years to come. Fuel cells, if you fuel them with a hydrocarbon fuel like natural gas or biogas, will produce a CO2 emission. But what's different from fuel cells and heat engines is that when they make CO2, it's before there's been any mixing with air. So it's very easy to extract the CO2. So it's possible to extract the CO2 from these platforms before it gets emitted. And I'll talk a little bit about that as we go along. The carbonate fuel cell, because of its unique electrochemistry, can actually capture CO2 from an external source. So we're looking at deploying that for carbon capture applications. Both of these fuel cells are very fuel flexible, and so they can run on hydrogen blends or pure hydrogen in the case of solid oxide. Solid oxide can be run in reverse as an electrolysis platform to make hydrogen. And if you think about storing that hydrogen and then using it back in a fuel cell, you start to enable some interesting long duration energy storage concepts. So these are the two electrochemical technologies that we're basically using to address the challenges and the opportunities of the energy transition. Just to give you an idea what some of this equipment actually looks like, this slide shows our carbonate platforms. And on the left, that fellow is holding a single carbonate fuel cell. So a fuel cell consists of a fuel electrode, an air electrode, and a thin layer between them called the electrolyte matrix. And on either side of those electrodes is a thin corrugated steel layer that allows for the flow of gases, the air gases on one side and the fuel gases on the other side. And then that cell will make electricity when it's provided with fuel and air. There are 400 of these cells stacked in the stack behind them, and that's our standard stack. And 4 of those stacks go into our standard module, which after DC to AC conversion and parasitics nets 1.4 megawatts. So one of those modules is used in our 1.4 megawatt platform, 2 of them in our 2.8 megawatt platform. We also have a platform that co-produces hydrogen along with power that uses 2 of those modules, and nets a little bit less, about 2.3 megawatts, because some of the power is used to compress and purify the hydrogen. And both of those platforms can be configured to co-produce carbon dioxide as well. And I'll talk a little bit about that. So that 2-platform system is the biggest system we make, but larger projects are done primarily by putting multiple units at a site. So at the lower right is the biggest project in the world. It's a 59 megawatt system just outside of Seoul, South Korea. And you can see a 14 megawatt and a 15 megawatt system in different towns in Connecticut that have been put together from multiples of the 2.8 megawatt platform. And the types of projects that have been done is, as I said before, it's a mix of what we call behind the meter, where the customer is making their own power and heat. And a good example of that is the project on the lower left. That's a 5.6 megawatt system at Pfizer's R&D facility in Groton, Connecticut. That system makes a good chunk of the power that they need. It also makes all the steam they need, so they've been able to turn off their gas-fired steam generators, so that enhances the sustainability. And the other advantage is that in the event of a grid loss, which is unfortunately frequent in that area, the system can continue to make power feeding a dedicated isolated load. And that's one of the key features of these systems, is the ability that they bring for resiliency. And to the upper left there is another project in South Korea. That's a 20 megawatt system that we operate, where we sell electricity to the local Korean utility. And the upper right is the 15 megawatt system in Bridgeport, Connecticut. We use waste heat in that system to make extra power in an organic Rankine turbine generator to enhance the sustainability and efficiency of that. And that's an example of one of the advantages of fuel cells. That's 15 megawatts in the middle of downtown Bridgeport, Connecticut. You know, you just couldn't put an engine generator or a gas turbine generator where we've put this system. And in the lower right is an interesting system that one of our local utilities, AvantGrid, has done, where they've put in one of our 2.8 megawatt systems and a 2.2 megawatt solar system. So we provide baseload power. The solar system provides peaking power. And what's interesting is that our system operates on about 1/4 of an acre, and the solar system operates on about 9 acres. And because of our high capacity factor, we produce many more megawatt hours per unit of space than the solar system. So we work very well with solar systems, and one of our advantages is that high output energy density. And a key feature, and the reason why people deploy fuel cells, is because of the opportunity for emissions reduction. And what this slide is showing is that if you look at the amount of emissions that are avoided, fuel cells are not zero carbon. They produce very, very low levels of things like NOx and SOx and particulates, but they're not zero, but they're orders of magnitude lower than typical power generation equipment. And lower than the utility grid, and that's the key thing. If you look at operating these fuel cell systems, even a fuel cell system fueled with natural gas is still producing less CO2 than the average US grid or many grids around the country per kilowatt hour. And so we avoid emissions while we run. We don't avoid as many emissions as wind and solar when they run, but we run around the clock and they don't. And so when you look at that effect, we can actually avoid more emissions, more CO2, more NOx, more particulates than zero emission wind and solar, just because of our higher capacity factor. So how can we apply this technology at treatment plants? And we see a lot of benefits to the use of this kind of technology at wastewater treatment plants. Obviously, the on-site production of clean power and heat has immediate benefits to the plant operator. And in many cases, that electricity produced is not only renewable, but it's less expensive than what's available from the utility. And largely that's because of you're using what is essentially a waste product, the methane from the digester, and you don't have to upgrade it to natural gas standards. You have to do some cleanup. And so in many areas, especially like California, that could produce more economical power than the utility. And so that stems from the utilization of on-site biogas. You avoid flaring, you avoid the emissions from other types of combustion-based generators like engines or microturbines that have NOx and particulate emissions that the fuel cells don't have. And the other thing, which I'll talk about a little bit, and this is kind of new to us, is the optional co-production of valuable byproducts. I mean, we've done, and I'll talk about them, some wastewater treatment projects, but they haven't yet had these features except for the first ones that we're introducing now, where in addition to power and heat, we can optionally produce hydrogen, carbon dioxide, and water. So I'll talk a little bit about those new features that we're introducing. So this is our approach to biogas, essentially, is we take the digester gas from the digester, and I'll talk a little bit about its constitution, but we essentially have to dry it out, take out the sulfur and the siloxanes. We can leave in the CO2 diluent and send that right to the fuel cell. The fuel cell produces electricity, and it also produces heat, and of course the digesters use heat. And a few slides down, I'll give an example of the amount of heat and power that matches with a certain size of digester. And so that's the key feature, is there's less cleanup needed compared to if you wanted to inject it into the natural gas grid. And as I'll talk about, carbonate in particular is uniquely suited to this because of its chemistry. So what are the differences between natural gas and digester gas? So we started thinking about commercializing carbonate fuel cells in the late 1990s and shipped our first commercial system in 2003. And we were designing these systems for natural gas. It's 90 to 100% methane, and the balance is usually higher hydrocarbons, 900 to 1,000 BTUs per cubic foot. It's very dry, almost never has any oxygen in it except areas that used to do peak shaving. And it's odorized for safety with a little bit of sulfur put in, typically 3 ppm, at most 20 ppm. And that sulfur is a poison to fuel cells, so we have to clean that out. So we have a system in every one of our platforms that cleans out that sulfur. If you look at digester gas, it's much more dilute. It's 50 to 80% methane. Most of the municipal wastewater treatment digesters are about 60% methane, 40% CO2. The higher concentration methane contents is what we see in, say, a brewery or a food processor digester. So that's 500 to 800 BTUs per cubic foot versus 1,000 for natural gas. It's typically 550 BTUs per cubic foot. It comes out of the digester saturated at the digester temperature, so it's high humidity. It can have oxygen from bleeding into the digester for some types of digesters, so it can have a little bit of oxygen in it. And the sulfur, instead of being up to 20 ppm, is hundreds of ppm or even higher, and it also contains siloxane. So as we started to commercialize based on natural gas, we got a lot of interest in using these systems in biogas systems because it's both methane fuel. You just have to deal with these differences. And in fact, as things rolled out, what happened is that first system that we shipped commercially in 2003, the customer told us relatively late in the development of the project by the way, I want to run this on my digester gas. So this was a project that was going to a Kirin brewery in Japan. And they told us fairly late in the development of the project that, we don't have line of sight to getting the LNG that we need to fuel this, but we do have a digester that we use to reduce our solid waste as we make beer. So we'd like you to run this on digester gas. So we took a look at it, and we realized that we had the capability to do that. We had to do some extra upfront cleanup that we put together. And that was our first commercial system. It was a 250 kilowatt system at that brewery in Japan back in 2003. And that was followed by a couple other projects at breweries, a few food waste digestion applications in both Japan and in the US, and a lot of municipal wastewater treatment plants. And so along that way, we learned what to do and what to not to do in this application. And we developed this advanced feature set. We had to make sure the systems had the flow capability to handle that lower BTU content and still make the rated output. We recognize that some of these digester sources fluctuate and are not 100% reliable. And we like to keep the fuel cell running. So we developed dual fuel features where if the digester output went down, we could augment it with natural gas and then blend back to the full digester gas when it became available. And the other thing that happened in some of our early projects is we relied on third-party suppliers to do the upstream gas cleanup, and some of them worked better than others. I'll just put it that way. So we realized that we really had to optimize that cleanup technology, and so we developed some proprietary biogas cleanup technology and also some proprietary methods for monitoring that biogas to make sure that we've really gotten all the sulfur out that we need to get out. So that's really helped us as we've addressed this market with some very unique capabilities. So here is like a summary of those advantages. The one thing I mentioned is that you don't have to upgrade the fuel to natural gas standards. You have to take out that water, you have to take out the sulfur and the siloxanes, but you can leave in that 40% CO2. And that's because carbonate fuel cells don't particularly care about that CO2. As I'll show in a couple slides, there's a slight performance impact for our solid oxide fuel cell, but the carbonate electrochemistry, there's one electrode that actually likes the extra CO2, and there's another electrode that has an impact. And so at net, there really is no impact of the CO2 dilution. I mentioned that we've developed these dual fuel capabilities that allow us to deal with the fluctuations coming out of the system. And the gas cleanup, we've really optimized that, primarily looking at reliability as the key thing. We don't want to have system issues that end up poisoning the fuel cell. And so it's kind of laid out there schematically in terms of the raw sulfur removal, compression and drying, siloxane and sulfur removal, and then polishing, and then it's ready for the fuel cell. And just to make sure that the gas is as clean as it needs to be, we've developed some patented approaches to making sure that to continuously measuring very, very low sulfur levels, because there wasn't off-the-shelf technology available. And so they're deployed primarily as combined heat and power platform. And as you know, there are plenty of uses for heat in a wastewater treatment plant. And I'll give you some examples of some of these systems deployed in CHP applications at wastewater treatment plants. So here's three of the most recent. There's a 1.4 megawatt system at the city of Riverside in California. And it essentially produces electricity for use on site by the city of Riverside. And as is almost always done in these projects, the waste heat from the fuel cell is used to support the anaerobic digester. The heat is fed back into the digester in a hot water loop. At San Bernardino, California, a very similar system, a 1.4 megawatt system. This is power that is consumed on site. The heat again supports the digesters. And at Tulare, again in California, that's a 2.8 megawatt system. In this particular case, Tulare already had on-site power generation. They didn't need the power, so we sell the electricity. The renewable electricity from the unit is sold to the into the grid under California's Biomat, which is a renewable feed-in tariff program. So different business models there. In the case of the other two, it's on-site power generation. It's reducing the utility offtake. In case number 3, we're buying the gas from Tulare and producing power that we sell under that feed-in tariff to the local utility. And so, like I said, 2 decades of biogas projects since that first one in 2003, more than 500,000 operating hours. And so we've had the time and the experience and the bruises here and there to really optimize the way these things interface with digesters. And we were the first distributed technology to be certified by CARB for operation on biogas at low emissions. So CARB, California Air Resources Board, runs a certification project for distributed generators. It has been in place for many years for natural gas fuel generators, and they started some time ago to certify biogas systems. And what they basically do is you have to have a third party test your emissions, and they certify that you're below some target emissions that they have around NOx and SOx and VOCs and carbon monoxide. And we have that certification for all of our platforms. And that map on the left shows the current and past projects. Like I said, we've been doing these projects for a long time. Some of them have just run their normal project life. We continue to do, we just announced one recently for Sacramento Sewer District. And so we continue to operate the units that we have there and expect to announce more projects as we go forward. So just a little bit of a technical discussion about the equipment. This is the specifications for the carbonate fuel cell power generation platform. We have 2, one that makes 1.4 megawatts and the other that makes 2.8 megawatts. And there's a lot of heat available for recovery, very low emissions. And both of these systems specifications are the same, whether it's running on natural gas or on-site biogas. This is the specification for our solid oxide platform. And you'll notice there's 2 different sets of specs, slightly different for natural gas versus biogas. Solid oxide doesn't have that advantage that carbonate has in terms of the electrochemistry not being affected by the CO2 dilution. So the efficiency drops down a little bit, but we can still make the same amount of power. The real advantage of this platform versus carbonate is we've found that we've had to walk away from a lot of opportunities at smaller digesters because the carbonate platform is just too big. So this platform at 250 kilowatts will help us address that market as we go forward. And just to give you an idea of the size matching of these systems to a digester, this is kind of an illustrative view of how much fuel a carbonate fuel cell makes as it makes power. So this is examples of a 1.4 megawatt system. It runs at 47% efficiency. So it needs about 3 megawatts of fuel. And that would come from, and this varies obviously depending on the type of digester, that would come from something on the order of a 45 million gallon a day digester. Would be a good match for a 1.4 megawatt system. That 1.4 megawatt system puts out more heat than is needed to support that amount of digester production, but typically we're matched to a digester that's much bigger than what we need, and so they need all the heat we can provide. So it produces 1.4 megawatts of power. In this example, 1.4 megawatts, a million BTUs per hour of heat supports the digester operation. There's about 2 million BTUs per hour of heat available for other applications, either if the digester is bigger or if there are other heat uses on site. So that's just an idea of the size of the equipment for a given size of digester. And now I'll talk a little bit about those applications I mentioned where we make additional co-products. And so this slide illustrates these 2 applications we call CO2 recovery and CO2 capture. In carbon recovery, that's what the name we've given to when we capture our own CO2. As I mentioned, we can grab the CO2 in the system before it gets mixed with air and purify it and export it before we emit it. And that's a really good application for a customer who uses CO2, because you're making 10 or 20 tons a day of CO2 from one of these systems. That's too little to really support a sequestration application. But for on-site utilization, it's perfect. So you can imagine these things running, providing power, heat, and CO2 to the process. And there's a list of potential applications there. We're talking to customers really in all those applications right now. One of them is water treatment. I know CO2 is sometimes used for pH adjustment, and so that could be another aspect of this that you might consider when you're looking at carbonate fuel cells being deployed at wastewater treatment plants. And on the right there is our second application, carbon capture. That's where we capture the CO2 from an external source, in addition to capturing our own CO2. And that can just produce more CO2, but it can also, if you've got on-site boilers that are gas-fed, it can help avoid the CO2 emissions from those. And right now we are offering that commercially. It requires a certain D rate for the power plant because of the energy required for the CO2 capture. And you may be aware that we're working with ExxonMobil to optimize the technology for larger systems and to improve the power output while we do CO2. But it is available today for smaller commercial systems that need CO2 from small gas-fired boilers. So that's the CO2 co-production. And this is an example of the hydrogen co-production. And this is a project that we are operating right now for Toyota at the Port of Long Beach, California. And at this port, Toyota is importing a lot of cars, but many of them are their fuel cell cars, the Mirai, and they're also doing a heavy-duty truck development and filling operation there. So they have a good on-site demand for hydrogen. So this system produces hydrogen for their vehicle fueling. It also produces power, and it co-produces water at the same time. And just to show you exactly how it fits together, the way our fuel cells work, whether it's natural gas or biogas, it's both methane fuels. The first thing that happens inside our stack is the methane is converted to hydrogen in a reforming reaction that's fed from heat and water from the fuel cell. It's a very efficient way to make hydrogen. And there's no combustion the way there is in conventional hydrogen production, and there's no water consumption. In fact, it's a net water producer. So that lack of combustion means lower CO2 emission and also lower criteria pollutants. And in the case of the Toyota project, we're fueling it with so-called directed biogas or book and claim biogas. And so it's renewable power. So this system produces up to 2.3 megawatts of electricity. Toyota needs a few hundred kilowatts of it, and the balance is sold to that same feed-in tariff that I mentioned before for the Tulare project, the biomat feed-in tariff. It produces 1,200 kilograms of hydrogen a day, and it also produces 1,400 gallons of water a day. And that was something we hadn't paid much attention to until we found out that Toyota has a major car washing operation at this facility. All the cars that come in need to be washed, and it is often in a drought situation. So the fact that we can reduce their city water consumption by 1,400 gallons a day is a significant enhancement to the sustainability of this particular project. And so very, very successful approach to improving the sustainability, a key part of Toyota's drive to make that a net zero operation at their port facility. And so really thrilled with getting this off the ground. This is the first full-scale commercial project with this technology that we call Trigen because of its production of power, heat, and power, hydrogen, and water. And getting back to wastewater treatment plants, we actually think that Trigen would be a really good application at wastewater treatment plants. And it may be the best value proposition because you enjoy the low-cost renewable fuel, and all the other advantages as far as minimal fuel upgrading required apply in this application. And the co-production of power and heat and water can support the water treatment facility operation. And the hydrogen offtake, there's a variety of different ways that can be utilized. Interestingly enough, the very first demonstration of this Trigen technology was a 250 kilowatt unit that was demonstrated at the wastewater treatment plant of the Orange County Sanitation District in Fountain Valley, California. using on-site biogas, and they actually had an on-site hydrogen filling station there. So this is an example, as there's more and more demand of hydrogen, this is another way that wastewater treatment operators can think of enhancing the value of that renewable fuel that they make while they're just doing their treatment operation. In addition to supporting their own power and heat and water needs, the ability to provide hydrogen can really enhance the economics of their operation.